Good evening, everybody. Today, today we today we're going to talk about today we're going to talk about the local seismic seismicity in Menengai. The project came out with a person who graduated 20 years ago in UTEP, and now he's the CEO of this company. His name is Simuji, and he gave the project to Anthony Walma, and he graduated 1 year. And the study base is in the East Africa Rift, and it's in a caldera called Menengai, southwest of Nakuru. It's very, very active. And Navasha shows you the plant that they're extracting all the steam to convert electricity on it. We deploy seismic sensors broadband because they will need innovation. They're really more into conductivity resistivity, but had no innovation in seismicity. So we deploy in private properties, in schools, and the property of the GTC, as you can see in these pictures. This map shows you the seismicity that is deployed since March until December. We got the data until running. For 2 years, we're going to acquire all the data seismicity. The blue line is the rim. The red line are the fault of the Kenya Rift. And this is the data status that we got, as mentioned, March and July is the phase 1. And then on phase 2, we got July and December. And we use a software package called Antelope. And we only have 3 stations with slightly 1 second time error. And we find out by looking at the waveforms, we use an automatic routine to determine the phases. And we find out there was a bending of the waveforms, and we thought was a tidal force, meaning inflation deformation of the caldera. And we use a histogram to analyze if it's true. But we find out we use the Pascal software package, and for every 4 hours there's a tidal force, and actually was a temperature variation going on. So it was not a tidal force at all. And the histogram just shows you the joule days versus, actually the slight error is the number of phases. So we did 3 detections, we did long periods, and we did E-emergent phases. And this is a summary of what's going on. Some of the station BH and R is vehicles passing through the road, and the sensor acquire what's going on. Some of the station was the temperature fluctuation going on, and also we did manually long periods. And this is for now. We have preliminary results for the relocation we have for the 13 seismic stations. And we find out around the relocation using HypoDD, which is relocation events, aligns really well on this model they've done in the conference in GTC, Geothermal Development Company, in November. This is kind of resistivity, and the events aligns around 1 to 2 kilometers depth, which is the red one is the hot magma of the caldera, and this is the results that we acquired. The triangles are the seismic stations, and these are the events of the relocation. This is another just explanation about we're doing for sure we're splitting. We're trying to do for teleseismic events, and there's a delay time of the waveforms using the north-south component and then east and west component of the broadband. And this is the preliminary results. We stack the teleseismic events, which is far away from the stations, which is 90 degrees to 150 degrees, and around every station has 45, 50 events, and we stack it and give you the orientation of the mantle flow. For now, we don't have which depth represents the direction. And for summary, of the first phase, we didn't acquire that much events. The second phase, that's, as I showed you, the relocation. We're waiting for the third phase. And for future work, David Sandwell and Bridget Hunter, they showed the department how to approximate INSAR. So we're trying to write a proposal for Germany to acquire from Menengai and do ScanSAR. And at the moment, we're developing the ambient noise tomography to get a better imagery going on in the internal of the caldera. And for the moment, I'm almost done with using Unix and seismic analysis code to finish the algorithm. And just acknowledge the faculty and then the GDC that did a good job on give us the data. So you guys have any questions?